Good day, sir. I am Engine Cadet Macas, together with my groupmates, Engine Cadet Tabalon, Engine Cadet Lereo, Engine Cadet Ruga, Engine Cadet Lim, Engine Cadet Dayama, and Engine Cadet Bitulan. We will report all about dual cycle. So stay tuned, and I hope you will understand it.
Good day everyone, good day sir. So today we're going to discuss about the dual cycle and how it works. So in the first slide you can see the picture of the engine. So I'm going to explain the internal combustion, what it do. So an external combustion engine or ICE is a type of engine that generates power by turning fuel inside the engine itself rather than in an internal furnace or boiler. So this is how it works. First is air and fuel intake. A mixture of air and fuel, typically gasoline or diesel, is drawn into a cylinder. Next is compression. The piston compresses the air-fuel mixture, making it highly combustible. Next is ignition. A spark in gasoline engine or heat from compression in diesel engine ignites the mixture, causing an explosion. Next is power stroke. The explosion forces the piston downward, creating mechanical energy. Lastly is exhaust. The piston pushes out the burn gases through the exhaust valve.
So let's talk about the dual cycle, also known as the mixed cycle, Trinker cycle, or Sabat cycle. It's a thermodynamic model that provides a more realistic representation of the combustion process in internal combustion engines, particularly modern diesel and some spark ignition engines. It bridges the gap between the ideal Otto cycle and the ideal diesel cycle by combining aspects of both. So let's talk about the Otto cycle and diesel cycle and dual cycles. So the Otto, diesel, and dual cycles are idealized thermodynamic models of internal combustion engines, differing primarily in how heat representing fuel combustion is added. So the Otto cycle, which is the constant volume, heat is added instantaneously at constant volume, mimicking spark ignition, which is gasoline engines, where a spark ignites the fuel-air mixture when the piston is at its highest point, leading to a rapid pressure increase. So the next one is diesel cycle, which is the constant pressure. Heat is added at constant pressure, modeling compression ignition, which is the diesel engines, where fuel is injected into hot compressed air and ignites, with fuel injection continuing as the piston moves down to maintain relatively. So the next one is dual cycle. So the dual cycle is constant volume then constant pressure. So this cycle combines elements of both with an initial phase of constant volume heat addition followed by constant pressure heat addition. It's a more realistic model for modern engines, especially high-speed diesels, as it captures both the rapid initial combustions and the most sustained burning phase, offering a balance between the high peak pressures of the Otto cycle and the higher efficiency potential of the diesel cycle.
Good day everyone, my name is Gideon Ezekiel Bidiama and I will report on the application of dual cycle. Dual cycle engine are types of internal combustion engine that combine the feature of either and diesel cycle to achieve higher efficiency and power output. They are widely used in applications such as marine propulsion, power generation, and aviation. For cycle analysis, the dual cycle models engine combustion with both constant volume and constant pressure heat addition. It consists of 5 steps: isentropic compression, constant volume heat addition, constant pressure heat addition, isentropic expansion, and constant volume heat rejection. Key parameters includes the compression ratio, cut-off ratio, and pressure ratio. The cycle thermal efficiency lies between the Otto and diesel cycles and depends on these ratio and the specific heat ratio. And that's all for my report, guys. Thank you for listening.
Good morning, everyone. My topic for today is all about cycle analysis. Cycle analysis of a dual cycle. Cycle analysis of a dual cycle. This is the air standard for a cycle for a modern fast-running diesel engine. First, the air is compressed isentropically, making it hot. Fuel injection starts before the point of maximum compression. After a short delay in which fuel accumulates in the cylinder, the fuel warms up to the air temperature and detonates, causing a sudden rise in pressure. This is ideally a constant volume heating process. Furthermore, injection keeps the fuel burning as the volume increases and produces a constant pressure heating process. After a cut-off, the hot air expands isentropically, and then at the end of the stroke, the exhaust valve opens, producing a sudden drop in pressure. This is ideally a constant volume cooling process. The air standard of a dual cycle models a diesel engine operations to isentropic compression and expansion phase interspeeds with constant volume and constant pressure heat addition rejection processes. This results in a net positive work output. The dual cycle is more realistic model than the Otto or diesel cycle because it accounts for both constant volume and constant pressure heat addition. The actual processes in a real engine deviate from the ideal isentropic and a constant volume pressure. Isentropic due to factors like friction and heat losses. Cycle process of a dual cycle. So the cycle consists of 5 processes. The first one is isentropic compression. So 1 to 2. Air is compressed isentropically, increasing its temperature. Next is constant volume heat addition, the 2 to 3 process. Fuel injection starts before maximum compression. After a delay, the fuel ignites, causing a rapid rise in pressure at a constant volume. The third one is constant pressure heat addition, the 3 to 4 process. Continued fuel injection maintains a constant pressure while the volume increases. Next one is number 4. Isentropic expansion, 4 to 5 process. The hot gases expands isentropically performing work. And the last one is constant volume heat rejection, the 5 to 1 process. So which is the reverse. The exhaust valve opens, causing a sudden pressure drop at a constant volume as a heat is rejected.
Understanding the dual cycle process is the dual cycle consists of 5 processes visualized best using pressure, volume, and temperature entropy diagram. So for the isentropic compression, state 1 to state 2, the air-fuel mixture is compressed adiabatically and reversibly, increasing pressure and temperature. Understanding the dual cycle process is the dual cycle consists of 5 processes visualized best using pressure, volume, and temperature entropy diagram. So for the isentropic compression, state 1 to state 2, the air-fuel mixture is compressed adiabatically and reversibly, increasing pressure and temperature. So for the next one is the constant volume heat addition. Heat is added at constant volume from state 2 to state 3, further increasing pressure and temperature. This mimics the initial rapid combustion phase. For the third one is the constant pressure heat addition. From state 3 to state 4, more heat is added at constant pressure, increasing volume and temperature. This represents the slower, later stage of combustion. For the fourth one is the isentropic expansion, state 4 to state 5. the hot gases expand adiabatically and reversibly, producing work because this is the power of stroke. So for the fifth one is the constant volume heat rejection, state 5 to state 1. Heat is rejected at constant volume, returning the system to its initial state.
Today, we compare the three fundamental thermodynamic cycles used in a thermal combustion engine, which is Otto cycle, the diesel cycle, and the dual cycle. Each cycle models the idealized process of different type of engines. First, Otto cycle is more efficiency than diesel because heat is added in constant volume, which is diesel cycle is less efficiency at the same comparison ratio, but typically operates a high comparison ratio, which improve the efficiency. And the last, dual cycle has efficiency between Otto and diesel. It balances performance and practically for a real-world engines. Next, we talk about thermal efficiency. What is thermal efficiency? Thermal efficiency is measure of how will a heat engine converts heat into useful work. It tells us what percentage of the energy from fuel is actually used. Move a piston, turn a wheel, or do anything mechanical work, and how much is wasted as heat of the surrounding. And thermal efficiency is a dimension of measure of how will a thermal device convert heat and into useful work or other form of energy. It's expressed as a ratio of the useful output energy to the input heat energy. This ratio is always less than 100%, as some energy is always lost due efficiency like friction and heat loss.
Good day everyone. I, Engine Cadet Makas, will explain the work example number 1. So, we have an example problem about an ideal dual cycle. So, here I will read it to you. So, an ideal dual cycle with an air as the working fluid has a compression ratio of 18 and a cut-off ratio of 1.3. So, the pressure ratio during the constant volume heat addition process is 1.1. At the beginning of the compression, the air temperature is at 35 degrees Celsius. The mass of air throughout the cycle is 0.1 kilogram. So, here is the required of the problem. A. The amount of heat addition at constant volume in kilojoules. B. The amount of heat addition at constant pressure in kilojoules. C. The temperature at state 3, state 2, 3, and 4, or the T2, the T3, and the T4. And D. The total amount of heat addition in the cycle in kilojoules. So, here's the important note. The value of Cp, or the constant pressure, is equals to 1.005 kilojoules per kilogram times Kelvin, and the K is equals to 1.4, are constant throughout the cycle. And now, let's proceed to solve the problem. So first, we must state the given of the problem. So the given is the compression ratio, or RC, is equals to 18. The cut-off ratio, or is equals to 1.3. The pressure ratio is equals to 1.1. The temperature 1 is 35 degrees Celsius plus 273 to make it Kelvin is equals to 308 Kelvin. And the mass of the air throughout the cycle is 0.1 kilogram. Also, the constant pressure is equals to 1.005 kilojoules per kilogram times Kelvin, and the K is equals to 1.4. So here is the illustration of the dual cycle. The process 1 to 2 is what we call isentropic compression. Process 2 to 3 is the constant volume heat addition. Process 3 to 4, constant pressure heat addition. Process 4 to 5 is isentropic expansion. And the process 5 to 1 to complete this cycle is constant volume heat rejection. So here is the formula for solving the dual cycle. So for the first required, which is the heat addition at constant volume, QA1 is equals to MCV times T3 minus T2. But we only know that the given value of temperature is only the temperature 1. How do we solve the QA1? How do we solve the QA1 if we didn't know the value of T3 minus T2? So first, we must solve the respective value of temperature 2, temperature 3, and temperature 4 to proceed to solve the heat addition processes. So in T2, we have this formula. T2 is equals to T1 V1 over V2 close parenthesis K minus 1. So T1 is given, which is 308 Kelvin times 18. So if you wonder where is 18, this 18 came from, let's go back to this formula. So compression RC is equals to V1 over V2. And we know that the RC is given the problem, which is 18. So it means 18 is also equal to V1 over V2. That's why we input the 18 here. So 308 Kelvin times 18 raised to the power of 1.4 minus 1 is equals to 978.72 Kelvin. So now we solve the value of temperature 2. Now let's proceed to solve that value of temperature 3. So T3 is equals to T2 close parenthesis P3 over P2. And if you wonder where this formula came from, it came from the P1 V1 over T1 is equals to P2 V2 over T2. We canceled out the V, which is volume, because it is the process where constant volume. So cancel out the volume. And to come up, we get the value of temperature 2. So substitute the value of temperature 2. So T2 here. So 978.72 Kelvin times 1.1. So if you wonder where this 1.1 came from, let's go back to this formula. So compression ratio is equals to P3 over P2. And at the problem, it stated the value of compression ratio. So 1.1 is also equal to P3 over P2. That's why we plug in the value of 1.1 here. So multiply it, 978.72 Kelvin times 1.1, we come up the value of temperature T is equals to 1076.592 Kelvin. And now we already solved the temperature 2 and temperature 3. To complete it, we solve the value of temperature 4. So T3, temperature 4 is equals to T3 V4 over V3. So we use the V4, we cancel out the pressure because it is the process where constant pressure. So canceled out the pressure. So we came up with this formula. T4 is equals to T3 V4 over V3. So from this formula given, let's go back to this formula. The cutoff ratio is equals to V4 over V3. So in the given question, it stated the value of cutoff ratio, which is 1.3. So 1.3 is equal to V4 over V3. So we just multiply the temperature 3 which we solved earlier, which is 1076.592 Kelvin times 1.3, which is the V4 over V3, or the cutoff ratio, is equals to, we got the value of temperature 4 is equals to 1399.5696 Kelvin. So now we already solved the temperature that we needed to solve the heat addition processes. Now let's move forward to solve the heat addition. So first is A, heat addition at constant volume. So we have the formula QA1 is equals to MCV T3 minus T2. So we use MCV here because we know it is constant volume. So we didn't know yet the value of the value of CB, but we do know the value of K and CP. So from the formula, K is equals to CP over CB, just derive it and we will get the value of CV. So now CV is equals to CP over K. So CP is equals to 1.005 divided by 1.4, which is the value of K. So we have the value of CV is equals to 0.718 kilojoules per kilogram times Kelvin. So substitute the value of CV here. So M 0.1 kilogram, CV is 0.718 kilojoules per kilogram times Kelvin, and the temperature 3, which is 1075.592 Kelvin, and the temperature 2 is 978. So 0.1 times 0.718 is 0.0718 kilojoules per Kelvin, because we cancel out the kilogram here, and now multiply the difference between T3 and T2 is 97.872 Kelvin. Then cancel out, multiply this one, then we have the value of heat addition at constant volume is 7.03 kilojoules. So we already get the value of heat addition at constant volume. Now let's proceed to heat addition at constant pressure. We have this formula, QA2 is equals to MCP T4 minus T3. We use CP here because this process in its constant pressure. So we plug CP here. So now substitute the given value. M is equals to 0.1 kilogram. CP is equals to 1.005 kilojoules per kilogram times Kelvin times T4, which is we get earlier 1399.5696 Kelvin, minus T3 1076.592 Kelvin. Then 0.1 times 1.005, we have the answer of 0.1005 kilojoules per Kelvin. Cancel the kilogram here because we cancel the kilogram, and the difference between T4 minus T3 is 322.9776 Kelvin. Then multiply this one, we have the value, we came up the value of constant pressure at heat addition at constant pressure, QA2 is equals to 32.62 kilojoules. So we already get the value of heat addition at constant volume and heat addition at constant pressure. Now to solve the overall heat addition throughout the cycle is simply add the QA1 plus QA2. So QA, the total heat addition, the total heat added is equals to QA1 plus QA2. So QA1 is 7.03 kilojoules plus QA2 32.62 kilojoules. So the total heat addition is, or the Q total, heat total is equals to 39.65 kilojoules. So we already solved the required of the problem. I hope that you get it. Thank you.